If you've taken a linear algebra course in the past, you've probably seen something called a matrix written out as a rectangular grid of numbers, right? So something that looks maybe a little bit like this, right? Just a rectangular grid of numbers, something like that. All right, so let's review this concept. First, grounding the idea in something we've already been using extensively in this course, and then we'll move on to discover an intuitive description of what matrices actually are. So first things first, all along in the previous videos, we've been using vectors, right? So we've had some vector equal to something like this. Maybe we'll have a two-dimensional vector here just with x and y coordinates. And so we wrote it out maybe as a column vector like this. And well, we've been doing all sorts of stuff with this, right? We've been doing vector operations and what have you. But turns out all along, this actually could be considered to be a 1. Let's actually use a different color here. A 1 by 2 matrix. Okay, a 1 by 2 matrix. So we can see that in essence, a matrix just provides a useful way of storing numerical components that have some relation to the axes of our coordinate system, right? So we know that with a vector, this value right here is some component on the x-axis, and this value right here is some component on the y-axis. So although we haven't specified the x or y-axis inside the vector or matrix, 1 by 2 matrix, right? We know that these values correspond to some x and y values. So again, if you've used matrices in a linear algebra course in the past, you've probably used them to solve some system of linear equations, right? So maybe we had something like, how about x plus 4y equals 8, and let's write another line equation here, and let's say that maybe we have 2x minus 4y equals, how about -2? So again, if you've used matrices to solve like a system of equations like this, we would have rewritten this system of equations just by using the coefficients for each term, right? So we'd say, well, this is really 1x plus 4y. And then down here for the second line equation, we have 2x, right? So just write the coefficient there, minus 4y. And then, well, we would write this as a matrix, put in some brackets here, and say that, all right, so this we'll use to represent the left side of the equation here. And then, right, so that becomes that. And then, well, of course, we could also do something like represent the right-hand side as a matrix as well, right? So, right, this is commonly done when working with these sorts of equations in a linear algebra course, right? So again, in this case, we can see that we're just using the matrix as a way of representing the coefficients of the line equations, or in other words, some values that correspond to either x components or y components, right? So in this case, everything on this column corresponds to x components, and everything on this column corresponds to y components. So in this course, we are going to use matrices as well, but primarily as a way to describe a transformation in our coordinate system. So let's first describe what we mean by a transformation, and then we'll see how matrices help us to describe them efficiently. So when we perform a linear transformation, we can think of it as the process of transforming the entire coordinate system. This is, let's call this the old coordinate system. We are going to transform this entire coordinate system into a new coordinate system. All right. And, well, really, we can think of this old coordinate system as being fundamentally described by its basis vectors. So again, doing a little bit more digging into some more linear algebra fundamentals here, but well, of course, we know that any vector that we can draw in this coordinate space can be defined as a linear combination of the basis vectors in this coordinate space, right? So, of course, and those basis vectors being just unit vectors lying, right on each of the axes of the coordinate system. That's a good way of visualizing where they are and what they mean. So here's the basis vector I. It just has it's a unit vector. It has a length of 1, or a magnitude of 1, I should say. It lies on the x-axis, and let's say we have j as well. J would be the other basis vector lying along the y-axis. And so, well, any vector in this coordinate space, doesn't matter which vector it is, can be described as a linear combination of these two basis vectors. And so, with that line of thinking, we can kind of think of this coordinate space as a whole as sort of being defined by these basis vectors, right? That's a good visual way of thinking about it. And we are only working in 2 dimensions here with only 2 basis vectors. But of course, in 3 dimensions, we'll just have a third basis vector. All right, so any linear transformation can be thought of as just a manipulation of these basis vectors such that they now describe a new coordinate system. So let me just show you exactly what I mean by that, right? So these basis vectors, right, we know that I is equal to the vector 1, 0, right? 1 on the x, 0 on the y, and j equals 0, 1, 0 on the x, 1 on the y. So what if we just changed these basis vectors to something a little bit different? Well, what could we achieve by doing that? What if let's aim at creating a scale transformation. So this is going to be a scale transformation, or you can think of it as resizing the coordinate space. So let's just kind of visually kind of imagine what we're trying to do here. We're just kind of let's scale everything up by 2. How about? In fact, because we're in Photoshop here, we can do this all visually, which is fantastic. So if we were to kind of scale everything up by 2, it would start to look a little bit like this, right? These vectors, their magnitudes would be doubled, right? So what if we defined this new coordinate system with the basis vectors? Right, so this will be I. What if we define this as, how about 2, 0? I is now going to cover this distance. All right, and will be defined at 2, 0. And j as well, it'll basically be kind of like, we can think about it as a scalar multiplication of this basis vector by 2. So j will now be defined, that's j, at 0, 2. All right. So again, just understand what we've done here is just manipulated the basis vectors in some way such that they describe a destination or a new coordinate system that we are trying to transform some vector or some coordinates into. All right, and what we're going to see here is that we can use a matrix to describe this transformation. All right, so bear with me for a few moments here. We will work through this process step by step, but this is what we're aiming towards. If I just get rid of this extra information here and just kind of rewrite that, well, I don't know about you, but that sure looks like a matrix to me, right? And so what we're going to find is that any linear transformation can be described using just a matrix. All right, so let's actually draw out a vector here that we're going to transform, and let's do this. Let's see this in action. Let's say we have the vector, let's say 2, 1, right? So 2, 1. that'll look like this, right? So 2 on the x-axis, 1 on the y-axis. And we are going to transform this vector into this new coordinate system. Or in other words, we are going to scale this vector using this particular matrix to describe the transformation. All right, let's see exactly how that works. Well, first, let's just go back to the fact. Let's just move this out of the way. Let's first just go back to the fact that this vector, along with any other vector in this coordinate system, can be described as a linear combination of the basis vectors. So quite specifically, what I'm talking about is we can create this vector just by taking some multiple of the, I should use this color down here, some multiple of the basis vector I, right, which is 1, 0, plus some multiple, get that yellow color there, so plus some multiple of the basis vector j, which is 0, 1, right? So let's just do that. Let's just solve this linear combination here, right? So first, it's just a simple scalar multiplication, a scalar vector multiplication, right? So 2 times 1, 2 times 1 is 2, 2 times 0 is 0, plus 1 times 0 is 0, and 1 times 1 is 1. Then we do our vector addition here and end up with 2, 1. Right, which is, of course, the vector that we started with, right? We're just showing here that any vector in this coordinate system can be described as a linear combination of the basis vectors. All right, so with that out of the way, let's actually just move this right down here so that we can keep track of that. With that out of the way, let's take our new basis vectors, and remember, we took those new basis vectors, I being equal to 0, and j, let's get that blue color, right? So j being equal to 0, 2, and we just wrote them in matrix form here, but really it was 2 vectors. Let's do this same linear combination using the coordinates of this old vector. Let's do this same linear combination, except using the new basis vectors that we're essentially storing in this matrix. Now we're going to have to do it down here. Let's get a different color. We're going to have to do it down here just because we're running a bit low on space, right? So we're going to have this new vector, let's call it v prime, is going to be equal to, right? So the old coordinates of the old vector, so that'll be 2 times the basis vector I, which is, it now has the value 2, 0, plus, all right, plus, and that is a 1, right? So 1 times j, 1 times j, which now has a value of 0, 2. Let's do the linear combination here, right? So 2 times 2 is 4, 2 times 0 is 0. I guess I should do this in the purple color just to keep things consistent, right? So 4, 0 plus 0 and 2. Do our vector addition here, and we end up with 4, 2 as the end result. All right, so v prime, or the transformed vector, is now at 4, 2. Let's draw that out. Or actually, you know what we're going to do? Let's just plot a point on this, on these coordinates at 1, 2, 3, 4, 1, 2. All right, so 4, 2, 4, 2. We think the transformed or the scaled vector should end up at this point. All right, let's see if we're right. And again, this is why I love Photoshop for this sort of thing. Let's just grab that vector, make a copy of it, put it over here, and scale it up so it's about twice the size as it previously was. And there it is, all right? Makes perfect sense. The scaled version of this vector lies precisely where we think it should after performing the new linear combination using the coordinates of the old vector, right? The coordinates of the old vector and the new basis vectors. And again, I just want to stress the importance of realizing here that, that these new basis vectors, we can store them in a matrix. We can just write them like this. And we're going to see in the remainder of this course, we're going to see transformations represented as a matrix, right? And let's always remember what this means. This matrix representing the transformation is just telling us where the basis vectors I and j, and potentially another basis vector as well if we're in 3 dimensions. This matrix just tells us where those basis vectors land after the transformation. All right, let's follow the exact same process and just quickly do a rotation just to demonstrate another very commonly performed linear transformation. So let's use the same process here to transform this vertex v to a new coordinate system where it has been rotated. And let's say it's going to be a counterclockwise rotation 90 degrees. All right, so it's got to do something like this. Do a 90-degree rotation counterclockwise. All right, so, well, we know visually what should happen to the basis vectors I and j. So let's redraw those basis vectors where they should land in the new coordinate system. So, well, if we think about it, right, I has got to, it's got to rotate 90 degrees counterclockwise, and it'll end up pointing up on the y-axis, right? Let's label those, right? So x and y, x and y. So the basis vector I is now pointing up on the y-axis. So I now looks like this. It's now 0, 1, and the basis vector j, well, again, let's just visualize what it's supposed to be doing. It does a 90-degree counterclockwise rotation, so now j is pointing this way. This is j. J is now, well, -1 on the x-axis and 0 on the y-axis. All right. So let's go ahead and do a new linear combination of the vector v here. All right, so using these original coordinates 2, 1, let's do a new linear combination here and try and find the position of v prime. So we're going to be taking 2 times the basis vector I, which is now at 0, 1, plus 1. Let's get that purple back. Right, so plus 1 times the basis vector j, which now lies at -1, 0. Let's quickly do the linear combination. So we end up with 0, 2, right? 0, 2 plus -1, 0. All right, let's do our vector addition, and we end up with -1, 2. All right, so we think that v prime should end up at -1, 2. That is what we calculated here as the result of our transformation. So that'll be -1 and 2, which will be right around here. Let's see if that is the correct answer just by grabbing this vector. Let's make a copy of it, and we're going to want to move this vector over here. Alrighty, let's do a 90-degree rotation here. I can actually just type this directly into Photoshop. -90 degrees will give me that counterclockwise rotation. Put it right at origin here. Now, of course, my drawing isn't absolutely perfect. However, we can see that this result does indeed make sense. And yeah, that is precisely where the rotated version of that vector would land. It would land at -1, 2. All right, so There's our intuition behind how to do linear combinations. Yet again, just stress the importance of the fact that linear transformations can be represented by a matrix which stores where the basis vectors should land when transformed into the new coordinate space, right? So let's just say the matrix is equal to this matrix right here. Now, before we leave this section, we do need to talk about the fact that the translation transformation involves actually a different process than what we saw in action for rotation and scaling. Okay, so translation, or in other words, the movement, right? The movement of a point from one location to another, right? And just describing that movement. This is not a linear transformation as it's formally defined in linear algebra. And the difference can intuitively be seen when considering what happens to origin during the transformation. All right, thinking about the process we were using for scaling and rotation, well, what would happen, for example, if we tried to, scale the origin to maybe 2 times its size or 3 times its size, or something like that? Did some sort of scaling operation to origin, which is the 0 vector, right? Well, what would happen to it? Absolutely nothing, right? It would stay at origin, and we can kind of visually intuit this just by looking at the coordinate system and kind of imagining what would happen here, right? If we scale origin, it's going to stay at origin. It's not going to move at all, right? Same thing would happen with rotation here. If we were to rotate the 0 vector at origin, well, where would it be in the new coordinate system? It would be in exactly the same place. It would still be the 0 vector, right? So all this means is that a linear transformation basically leaves origin alone. It just leaves it where it was. With translation, on the other hand, we would expect origin to move along with every other coordinate when it is transformed. And let's just visualize that for a second, right? If we were transforming this vector here defined by this blue arrow, and let's say, well, maybe 1, 2, 3. What if we move it about 3 units? About 3 units in the y direction. Well, the results of this transformation is almost as though we've completely redefined this coordinate system up here, 3 units up in the y-axis, right? So really the only thing we're trying to see here is the fact that, well, this coordinate and every other coordinate, well, yeah, they're all going to be translated up 3 units on the y-axis, but the point is origin is translated as well, right? So this fact means that translation is not a linear transformation. It's actually a whole lot more simple than what we've been doing so far. Translation simply involves a simple vector addition. So, in fact, let's just see that in action just to see how that makes sense, right? So, yeah, let's say this vector. Get that blue color and say this vector was defined at, how about it was 2, 2, and we wanted to move that up 3 units on the y-axis, right? All we're really doing here is just saying that the transformed vector is equal to, the original vector. Just grab that blue color. So 2, 2. Plus, some change in x and some change in y. So the change in x is 0 and the change in y was 3, right? So it's just a simple vector addition. So we just sum across the rows here. So we'll end up with 2 on the x, that has not changed, and 5 on the y. Let's draw that out. So maybe let's get that green color back here. So 1, 2, 3, 4, 5. So v prime would now be positioned at 2, 1, 2, 3, 4, 5. It would be up here, essentially, right? And well, if we consider that to be a displacement from origin, sure, we will draw that, we'll visualize that line segment from origin. But the point is that every old coordinate, including origin from the old coordinate system, has been translated up 3 units on the y-axis. Okay, so translation is a vector addition. It doesn't involve multiplication. It does actually pose a significant challenge when trying to reconcile translation with rotation and scale and have these operations occur inside a 3D graphics application, all using the same mathematical operation. But we'll handle that, again, that reconciliation of these 3 types of transformations. We'll handle that in a future video. For now, we have our fundamental understanding of what's happening when we perform these various transformations. Next, we need to discuss some common matrix operations which will help us work with matrices in computer graphics.